The second chapter is moment. What is moment? Moment is turning tendency of a force. It is the product of force and it is the product of force and perpendicular distance between the line of action of the force and the point about which you want moment. Now in the figure, a force F is acting at point A and you want to find out the moment of this force about point O. The distance between A and O is D. So the moment is F into D, and the direction of the moment, that is the sense of the moment, is anti-clockwise, because this force will try to turn this member about point O in the upward direction. So that's why the sense of the moment is like this. Now moment is denoted by capital M, and because we are taking moment of this force about point O, that's why it is denoted as MO. MO. Now unit of moment is Newton into meter. Now refer this the second figure in which a force of 10 Newton is acting. I want to find out the moment of this force about this point O. Now the perpendicular distance between the line of action of this force and the line passing through the point O is 3 meter. That's why the moment is 10 into 3 equal to 30 Newton meter, and it is not 50 Newton meter. So this is 30 Newton meter instead of 50 Newton meter. Now in the third figure, a force of 20 Newton is an inclined force of 20 Newton is acting at point A, and I want to find out the moment of this force about point O. So because this is the inclined force, the force is inclined at 30 degree to the x-axis. So what I will do, I will resolve this force into x direction and y direction. Now in the x direction it is 20 cos 30 degree, and in the y direction it is 20 sin 30 degree. Now because the line of action of x component passes through the point O, therefore the perpendicular distance between this line and the point O is 0. That's why the moment of this force is 0. That means if the line of action of a particular force passes through the point about which you want to take the moment, then the moment of this force about this point is always 0. Now, moment of this force, that is 20 sine 30 degree, is 20 sine 30 into 5, because the perpendicular distance between this line and this line is 5 meter. So it is 20 sine 30 into 5, and the value will be 50 Newton meter. Now moments are of two types. One is clockwise moment, another is anti-clockwise moment. Now this figure shows a anti-clockwise moment and this figure shows a clockwise moment. Now I want to take the moment of 10 Newton about point A. So it is MA is 10 into 5, 50 Newton meter. And the turning tendency of this force about point A is like this. That's why this is anti-clockwise moment. Now I want moment of this 5 Newton force about point B. So MB is 5 into 8, 40 Newton meter. And the turning tendency of this force about point B is in this direction. That's why this is the clockwise moment. Geometrical representation of geometrical interpretation rather of moment. Geometrically, a moment is defined like this. Suppose a force F is represented by the line AB in magnitude, and I want to find out the moment of this force F about point O. Now what I will do, I will complete the triangle OAB by taking the line AB as the base. Then the moment of F about O is given by 2 into area of this triangle OAB. Suppose I want I want to represent the moment of this force. Let us say I have a 10 Newton force. This is the 10 Newton force, and I want to find out the moment of this force about this point A. So what I will do, I will convert this force into into a line scale. That is, I will choose a scale of, let us say, 1 centimeter equal to equal to 5 Newton. Then I will draw a 2 centimeter. So 10 Newton will be 2 centimeter. I will draw a 2 centimeter line, and the distance between this is, let us say, 5 meter. So I will choose the scale as 1 centimeter is 1 meter. Then I will take 5 centimeter, the point A, 5 centimeter from this line AB, and then uh, let us say this point is A1. Then I will join this line and form the triangle. Now then, what is the moment of this force, this force of 10 Newton about point A1? About point A1 is is MA1 is represented by MA1, and that is equal to 2 into area of triangle A1AB, area of triangle A1AB. This will give you the the moment of this force about point A1. So this is the geometrical represent interpretation of the moment. For details, you can read the article 3.3 of A.K. Upadhyaya Applied Mechanics book. Now next is principle of moment. What is principle of moments? Principle of moment says that algebraic sum of moments of all the forces acting on a body should be equal to 0. Now, what is the statement? If a body is in equilibrium under the action of number of forces acting simultaneously on a body, then the algebraic sum of moments of all the forces about a point is 0. This is principle of moments. Now, mathematically, it is represented as summation of m is equal to 0. Summation means algebraic sum of all the moments of the forces about points should be equal to 0. Now, uh, just refer this figure. There is a plane, and in this plane, four forces are acting: F1, F2, F3, and F4 acting. I want to find out the moment of these forces about point O. Now, the distance of these forces from point O is d1, d2, d3, and d4. Now, moment of this force about this point is F1 d1, and I'm considering the I'm considering anti-clockwise moment as positive. So obviously clockwise moment will be negative. Now F1 D1 is giving an anti-clockwise moment, so that's why this is positive. Now F2 D2 will be again anti-clockwise, so that's why this is positive. F3 D3 is clockwise, that's why this is negative, and F4 D4 is clockwise, that's why this is negative again. So, so algebraic sum of moments of all the forces. Why I'm saying algebraic sum? Because this in algebraic sum you will get plus sign as well as negative sign. So moment of all these forces about point O is summation of MO is equal to F1 D1 plus F2 D2 minus F3 D3 minus F4 D4, and according to the principle of moment they should be equal to 0. Now from this we will get F1 D1 plus F2 D2 is equal to F3 D3 plus F4 D4. Now F1 D1 plus F2 D2 is nothing but sum of anti-clockwise moments, and F3 D3 plus F4 D4 is nothing but sum of clockwise moments. So we can define principle of moments in another way as sum of clockwise moments is equal to sum of anti-clockwise moments of all the forces acting on a body. Now next is varignon's theorem. What is varignon's theorem? If a number of coplanar forces are acting on a body, coplanar, when the forces which are acting on the same plane. So if a number of coplanar forces are acting on a body, then algebraic sum of then algebraic sum of their moments about a point in their plane is equal to the moment of their resultant about the same point. So the what the Varignon's theorem says that the moment of the forces about a point is equal to moment of the resultant about the same point. Now here F1 and F2 are the two forces acting on a body. Let R be the resultant of these two forces. Uh, the distance of F1, F2 and R from point O is D1, D2 and D respectively. Therefore, the moment of these two forces about point O will be F1 D1 plus F2 D2. Why it is plus? Because both are the sense of moment of these two forces about point O is clockwise. Uh, Sorry, it is anti-clockwise. So I am taking anti-clockwise as positive here. Anti-clockwise positive. So because F1 D1 is anti-clockwise and F2 D2 is also anti-clockwise about point O, that's why F1 D1 plus F2 D2. And that is equal to R into D. Again, R into D is anti-clockwise. That's why again this is positive. So according to the variance theorem, R into D is equal to F1 D1 plus F2 D2. That is the moment of the resultant is equal to moment of the forces at point O. Now it is up to you whether you are taking clockwise moment as positive or anti-clockwise moment as positive. It entirely depends upon you only. Now proof of the variance theorem. For this you need to draw the figure again here. Drawing this figure again. This is a parallelogram. This is the point O. This is the diagonal. This is the resultant force R. This is the force F1 and this is F2. This is point O, A, B, C and D. Now let two forces F1 and F2 be represented by the sides AB and AD of this parallelogram ABCD. Let R be the resultant of these two forces, which is represented by the diagonal AC. O be the point about which we want to take the moment of all these forces. Now what you do, you join OA, OB and OD. Now from the figure, uh, area of triangle ABC equal to area of triangle ADC, because we know that the diagonal of a parallelogram divides it into two triangles of equal area, and area of OAB equal to area of ABC, because both the triangles are on the same base AB and are between the same parallel line AB and OC, therefore their areas are equal. Now from these two equations, what you will get area of OAB equal to area of ACD equal to area of ABC. So area ABC equal to area ACD equal to area AOB. Now moment of F1 about point O is 2 into area of triangle OAB, because triangle OAB is made up of the force F1, and moment of F2 about point O is 2 into area of triangle OAD, and moment of R about O is 2 into area of triangle OAC. Now I want now sum of the moments of force F1 and F2 is equal to 2 into area OAB plus 2 into area OAD. Now area OAB is equal to area ADC, as you can see from here. Area ADC equal to area OAB, area OAB. So instead of OAB you write ADC. So twice of area ADC plus twice of area OAD. Uh, Now if you take 2 common, what you are getting, we are getting area ADC plus area OAD. Now from the figure, area ADC plus area OAD is equal to area OAC. So that's why it is twice of area OAC. And what is twice of area OAC? This area is made up of the resultant R, or this triangle is made up of the resultant R. Therefore, this is nothing but the moment of R about point O. Now, parallel forces, like parallel forces and unlike parallel forces. Now, any number of forces are said to be parallel if their line of actions are parallel. Now, in this three forces, the line of action of uh, these forces are parallel. That's why these three forces are said to be parallel forces. Now, like parallel forces, if the line of action of the forces are parallel and the forces are acting in the same direction, then this type of forces are said to be like parallel forces. Now, unlike parallel forces, if the forces are acting in opposite direction and the line of actions are parallel, then this type of forces are said to be unlike parallel forces. Now, next is coupling. Couple is a pair of two equal and unlike parallel forces acting on a body. Now, the figure shows a couple. Now, here the forces are of equal magnitude and the distance between the forces is d. Uh, this distance is known as arm of the couple. Is known as arm of couple. Known as the arm of the couple. So, what is the moment of this couple? Moment of this couple will be one of the forces into the arm of the couple. So it is F into D. What is the resultant moment of this force system? The resultant moment will be F minus F is equal to 0. That means a couple has a resultant moment, but it doesn't have a resultant force, which you can see from here. Now, properties of couple. What are the properties of couple? A couple has no resultant force, but it has resultant moment, which you can see from above. I've already explained. Now, property number two, a couple cannot be replaced by a single force. Now, simply you can say the moment of the couple is Newton. So a Newton meter cannot be replaced by Newton only. So a couple cannot be replaced by a single force. Number three, any two couples of equal moment and sense are equivalent in their effect. That means this, if you have a couple acting on a body, you can replace this couple by another couple if its moment is same and the sense is also same. Then their effect on the body will be same. In this two figure, uh, the moment of this couple is 50 Newton meter, and what is the sense? Sense is clockwise. Here also, the moment of this couple is 50 Newton meter, and the sense is again clockwise. That's why this couple, the effect of this couple and this couple on a particular body will be the same. So you can replace this couple by this couple. So any couple can be replaced by another couple if the moment is same and the sense is also same. Any number of coplanar couple can be replaced by a single couple whose moment is equal to algebraic sum of moment of individual couples. In the figure, you can see there are three couples. Now, the sum of moment of these two couple, the sum of moment of these two couples is equal to the moment of this couple, then these two couple can be replaced by this couple, provided the sense of all the three couples are equal. Now here, what is the moment of this couple? The moment of the couple is 15, and moment of this couple is 40. Now, because the sense is clockwise in both the cases, so if you add, we are getting 55 Newton meter clockwise. And moment of this couple is also 55 Newton meter, and the sense is also clockwise. That's why these two couple can be replaced by this single couple. Property number five. The algebraic sum of moments of the forces forming a couple about a point in their plane is constant. Now you can see that the moment of the couple depends upon the force into the arm of the couple. It doesn't depends upon the point you want to take the moment of this couple. Now in this figure, the moment of this force about O is F into A, and the sense will be clockwise. So I'm taking clockwise as positive. I'm taking clockwise moment as positive. So what is the sum of moment of these two forces? So this is positive. Now F into OA is the moment of this force about point A, about point O, minus F into OB, because the sense is here anti-clockwise. So F into OA minus F into OB. Now if you calculate, you are getting F into OB, because OA minus OB is AB. So F into AB. So the moment of this couple about point O is F into AB. Now I've taken the moment, the point O within the arm of this couple. Now, what is the moment of this couple? F into OA. Again, it is clockwise, so positive. And F into OB. Again, it is positive. So F into OA plus F into OB. Now, again, you are getting F into AB. Now, I'm taking the point O on the other side of the couple. So, moment of this force about point O is F into A. Now here the sense of this for sense of this moment of this force is anti-clockwise. That's why it is negative. So F into A negative and F into OB. F into OB is clockwise. That's why it is positive. So F into OB minus F into A. Now finally you are getting F into AB. So from these three you can see that the moment of the couple depends upon the force into the arm of the couple. It doesn't depends upon the point about which you want to take the moment. Now, conditions of equilibrium. When you say that a body is in equilibrium, when a number of forces are acting on a body, the body is in equilibrium, this means there is no unbalanced force acting on the body. That is the resultant of all the forces acting on the body is zero. Suppose you have a body, and in this body, number of forces are acting. Now, when you will say that this body is in equilibrium, when the resultant of all this force system is zero, and the resultant is zero, if the resultant of all this force system is zero, then you can say that the body is in equilibrium. So the conditions of equilibrium are resultant is zero uh, means the algebraic sum of moments of all the forces along x-axis, that is sigma h, is equal to zero. Algebraic sum of moments of all the forces about the y-axis, that is sigma v, equal to zero. So if h is zero and v is zero, then you can easily say that r is zero. Resultant is zero, because you know that r is under root of sigma v square plus sigma h square. This you already know it. Sigma v square plus sigma h square. So for r to be zero, both sigma v and sigma h is to be zero. And the third condition is sigma m, that is the moment of all these forces about any point, let us say about any point O, should be zero. So the conditions of equilibrium are sigma h is equal to 0, sigma v equal to 0, and sigma m is equal to 0. Now, types of loadings. Loads are of the following types. Number one is concentrated or point load. Number two is uniformly distributed load, which is abbreviated as UDL. And number three is uniformly varying load. Uniformly varying load is not in your course, so we are concerned with the point load and the UDL. Now, what is point load? If a load is acting at a point, then you can say that a point load is acting on a body. Uh, this figure shows this point load. Now, uniformly distributed load. If the load is uniformly distributed over the length of a member, then it is said to be the uniformly distributed load. Rectangular loading is the example of this type of load. Now, the figure shows the UDL. Here you can say the bumps are of equal heights, and the entire member, that is the beam, the entire horizontal member is loaded with UDL. And UDL is denoted by uh, the unit of UDL, or the intensity of loading of UDL is Newton meter, Newton per meter. So it is generally denoted by small w. So small w Newton meter is the intensity of this UDL. Now you can convert this UDL into a point load by by finding out the area of this figure, because it is a rectangular loading which I have shown here. So the area of the rectangle, you know, is W into L. So this height of the rectangle will show the intensity of loading of UDL, and this is the length of the member over which the UDL is distributed. So the magnitude of the load will be W into L, which is the area of the rectangle, and the position of the load will be at the center of the rectangle, because we know that the CG of the rectangle lies at the center. That is the point at which the two diagonals intersect. So the position of the point load is very essential. Uh, when you are converting a UDL into a point load, then the position of this point load is very essential. So the position, if you want to replace this UDL by a point load, so the magnitude of the point load will be WL. This is the length L, will be WL, and the position will be at the center, that is L upon 2 on both sides. L upon 2 on both sides. Very essential. Now, uniformly varying load. How to convert the uniform? What is the uniformly varying load? If a load varies at a uniform rate from one point to another, then it is said to be a uniformly varying load. You can see in this figure, the load is varying uniformly. Now, this is the final intensity of loading, which is W Newton per meter. Now, triangular loading, trapezoidal loadings are the examples of uniformly varying load. Now, trapezoidal loading is shown like this. This is the trapezoidal. Now, the loading is shown like this. You can see it is varying uniformly. Now, how to convert this type of loading into a point load? Simple. You find out the area of the figure. Here the figure is a triangle. Here the figure is a trapezoidal. Now the area of this figure of this triangle is half W into L. Well is the length of the beam, that is the horizontal member. This length is L from here to here, and this is the height of this triangle, which is the intensity of loading also. Now, uh, now the magnitude of the point load will be half WL, and the position is at the CG. We know that the CG of a triangle lies at L upon 3 from the base. So the position will be L upon 3. L upon 3. So the position will be at L upon 3 from this side.